every computer you've ever touched. The phone in your pocket, the laptop on your desk, even the fastest supercomputer on the planet works on the exact same basic principle. This one doesn't. It doesn't compute in ones and zeros. It doesn't even fully make sense to the physicists who build it. And it might be the most misunderstood machine in the world right now. So let's fix that. What is a quantum computer, actually, and what can it really do? To understand what makes quantum computers different, we need few seconds on how every normal computer works. Every calculation your phone has ever made. Every photo you've opened. Every game you've played comes down to bits. A bit is just a switch. It's either on or it's off. We call that 1 or 0. String enough of these switches together, flicking on and off billions of times per second, and you get everything from a calculator to a supercomputer that can model the weather. It's an incredibly powerful idea, but it has one hard limit. At any given moment, each switch is only ever in one state. On or off, never both. That limit is exactly what quantum computers break. In a quantum computer, the basic unit isn't called a bit. It's called a qubit, short for quantum bit. And a qubit doesn't just sit at 0 or 1 like a switch. While it's processing, it exists in what's called a superposition, a combination of both 0 and 1 at the same time. Here's a useful way to picture it, though it's not a perfect analogy. Think of a spinning coin instead of a flipped one. While a coin is lying flat on the table, it's clearly heads or tails. But while it's spinning in the air, it's kind of both. Its final state isn't decided until it lands. A qubit works something like that. It holds a mix of possibilities while it's being processed and only lands on a definite 0 or 1 when it's measured at the end of the calculation. This is important and worth saying clearly. A quantum computer is not just a much faster regular computer. It's not trying harder versions of the same math. It's using an entirely different kind of physics to explore problems in a completely different way. Superposition alone isn't what makes quantum computers powerful. The second ingredient is something called entanglement. When two qubits become entangled, their states become linked. Measuring one instantly tells you something about the other, no matter how far apart they are. Einstein famously distrusted this idea, calling it spooky action at a distance. But it's been tested repeatedly in labs since the 1970s and 80s, and it holds up. It's real. When you link many qubits together through entanglement, they stop behaving like separate switches and start behaving like one interconnected system. That system can represent an enormous number of possible combinations simultaneously. And it's this combination of superposition and entanglement that gives quantum computers their real power for a narrow set of problems where this approach helps. Here's where a lot of people get the wrong idea. Quantum computers are not going to replace your laptop. They're not faster at browsing the internet, editing a video, or running most apps you use every day. For the vast majority of everyday computing, a classical computer is still better, cheaper, and more reliable. What quantum computers are genuinely good at is a specific category of problem. Ones involving enormous numbers of variables interacting with each other, the kind of problem that would take a classical supercomputer an impractical amount of time to brute force through. A major target is chemistry and materials science. Simulating how molecules and atoms interact is naturally a quantum problem, since molecules themselves obey quantum mechanics. Researchers are exploring quantum computing to help model new drugs, new batteries, and new materials, though, as of now, This remains largely experimental and complementary to classical simulation, not a wholesale replacement for it. Another major area is cryptography. Some of the encryption protecting today's internet relies on math problems, like factoring extremely large numbers that are practically impossible for classical computers to solve in a reasonable time. A sufficiently powerful, fault-tolerant quantum computer could, in theory, solve those problems far faster. That's why governments and companies worldwide are already developing post-quantum encryption standards, well ahead of quantum computers actually being capable of this. There's also optimization. Problems like finding the most efficient route among thousands of variables, something logistics companies, airlines, and financial firms are actively researching quantum approaches for, alongside continued advances in classical algorithms. So, if this all sounds incredible, why isn't every company using one already? Because quantum computers today are still early, fragile, and expensive. Qubits are extremely sensitive. The smallest vibration, temperature change, or stray bit of electromagnetic noise can cause them to lose their quantum state, a problem called decoherence. That's why quantum computers have to be cooled to temperatures colder than deep space, just above absolute zero, inside refrigerators like this one. Today's machines are also error-prone. Companies like IBM, Google, and others are in what's often called the noisy intermediate-scale quantum era. Machines with a few hundred to a few thousand qubits that still make frequent errors, long before we reach the millions of stable, error-corrected qubits that true large-scale applications would need. That doesn't mean the field isn't moving. It's moving fast. New milestones in qubit count, error correction, and stability are being announced regularly. But we're still in the early foundational stage of this technology, much like classical computers were in the era of room-sized machines built from vacuum tubes. So that's the real answer. A quantum computer isn't a faster version of what you already have. It's a fundamentally different way of processing information, one built on superposition and entanglement that's genuinely powerful for a narrow, important set of problems, and still very much in its early days. Now that you know what one actually is, in our next videos, we're covering more topics related to quantum computers. Hit subscribe button and keep watching.